my name is Atsuro Hoshino, and today I'm talking about Nash, which is an experimental tracing JIT virtual machine for GNU Guile. And so tracing JIT is a technique used in virtual machines to improve performance, and now I'm showing a brief demo. The program currently running is showing the ASCII mandible set for 20 times, and each set has a loop. The loops are nested, like each line showing the characters and so on, and it takes about 90.28 seconds. And now I'm running the same program with tracing option turned on. Runs in 0.37. That's fast. I suppose it's 2.1.3, but I update the Git I made from Git branch, so I'm not actually sure. So, a tracing JIT. Tracing JIT has some assumptions to achieve performance improvement, and one is that the program spends most of the runtime in loops. Typical tracing JIT has a bytecode interpreter, and the interpreter observes the bytecode instruction and seeks for the hot loops. And the instruction inside the detected loops are recorded and then further compiled to native code. And another assumption is that the several loops takes the duration of this similar code path. To achieve performance, we need to execute the compiled native code instead of bytecode. So compiling once, never executing won't make the performance improvement. I know that. Okay. So some key terms in tracing JIT are a trace, which is a recorded instruction sequence. In most cases, the sequence is recorded from a loop, and typical tracing JIT virtual machine has an interpreter, I said, which counts the number of loop iterations. And the iteration count has a certain threshold number. And after passing that threshold, the loop is detected as hot, and the interpreter starts tracing and recording the instruction. And a fragment is an artifact made from a trace. It contains the native code and some meta information to help the virtual machine. And the guard is a test inserted to native code. Because the recorded instructions are derived from a loop, we need to exit from that loop at a certain point. And the guard inserts a test with a condition appeared at the time of recording. And then when test fails, the virtual machine will fall back to the bytecode interpreter instead of executing the native code. Okay, so and we are proceeding to Guile. I suppose most of you know, but Guile is an implementation scheme, and it can run other languages than Scheme, but probably the Scheme is the most widely used and mature implementation. Guile compiles Scheme source code to bytecode. And the compilation could happen ahead of time when running a script, or could happen incrementally when running in REPL. Now I'm showing the mandible function that I ran in demo. It takes two arguments, x and y, and the procedure has a loop here. And the loop contains two comparisons. One comparing max iterations on variable I, and another a bailout variables and sum of zi and zr2. And the code on the right side is the disassembled bytecode of the mandible procedure. And we can see that bytecode has flat structure, and the bytecode contains labels, which is colored in red, L1, L2, and L3. And compiled bytecode instructions are interpreted by a C function, which is named virtual machine engine, VM engine. The C function has the bytecode instruction definitions, which are defined with using the C macros, VM define up. And engine could be viewed as a huge switch and case statement. And now I'm proceeding to the Nash overview. And Nash is designed as a drop-in replacement of that VM engine C function. The diagram showing a control flow of Nash running a user program. And the control flow has three key components. One is interpreter, then compiler, and native codes. The first user program starts from the interpreter. While it interprets the bytecode, the interpreter observes each bytecode instruction and seeks for hot loops. Certain instructions are treated as loop beginning instructions, such as the backward jumps and function calls. And Nash interpreter runs slower than Go's plain bytecode interpreter in this phase because it needs to detect the hot loops. And when hot loop was detected, the interpreter looks up the accompanying native code, which is here. But in the beginning, there's no native code yet, so the interpreter starts recording the instruction in the loop. This is a bytecode of the Mandelbrot. And using this as an example, for instance, the BR minus 23 at IP41, colored in red, is a backward jump instruction. The interpreter detects that it's a backward, and it jumps back to the 41 minus 23, which is 18, colored in red. And then it continues recording the instruction until it reaches to the point where the loop started, which is the 41. And the recorded trace is like this. Note that in the disassembled bytecode, the IP are rated numbers, but in recorded trace, it's absolute values shown in hex. So the recorded instructions are then passed to the compiler. The compiler is written in Scheme and it uses a normal form, IR, internal representation, and the compiler uses a JIT library code. Maybe you know GNU Lightning as backend. Here's a recorded trace. And this is the contents of internal representation. It has a prologue section, which is colored in blue, and a loop body section in red. The IR2 native code compilation is done almost straightforwardly. There's not much optimization done right now. Then after the compilation, we have the native code, so the control flow goes back to the interpreter after this pass. And at the moment, not all of the bytecode instructions are understood by the compiler. Some are tricky to implement. I haven't done yet. And when Nash finds those unimplemented bytecode, it just falls back to the interpreter. The interpreter will find the native code of the loop this time because it's already done. And it is likely to encounter the beginning of the loop immediately after the compilation because the user program is still inside the loop. The native code runs until the guard fails, and the guard failure will trigger the bailout code. The bailout code is a special code to recovers the virtual machine state and passes back the control of user program to the interpreter. And now showing the internal representation A normal form again on the left side. And the native code of loop body and x86 64-bit version. And I said that the mandible procedure has two comparison. One was comparing the variable I with max iterations, and another compiling the variable named bell out was sum of zi and zr2, which is shown in red right now. So how well does Nash performs? The graph showing results from running scheme cross-platform benchmark suit with Guile and Nash. And the benchmark suit contains 57 programs, and the results are normalized to the Guile's bytecode interpreter. Lower values are better, and the values under 1 mean that Nash performed better than Guile bytecode interpreter. And Nash ran 52 out of 57 programs faster than Guile's. So it means that 5 of the programs run slower than Guile's bytecode interpreter. Top 3 benchmarks with improvement rate were the sum FP and Embro and sum. And sum run about 40 times faster and Embro about 30 times. These two programs contains a tight loop with floating point numbers. And Nash could perform the loop computation in the loop without boxing it, the floating point numbers. But in Guile and typical scheme implementations, those floating point numbers are implemented with heap objects, so it takes some time. The sum program runs about 8 times faster. It does not contain those floating point numbers, it's just a simple fixed number addition, but it's still faster. And the string benchmark was slower. The benchmark program contains lots of string append and substring as string-related computations, and those computations are implemented in C and Guile. So, and Nash also calls the same C functions, so there's not much difference in this case. Similar thing could be said to CTAC and FibC, which is the recursive TAC and Fibonacci function implemented with call with continuations. And the parsing and dynamic. Those two programs contains a large amount of data-driven conditional branches, which is known that tracing JIT does not work well. The next graph is showing the geometric standard scores of the benchmark suit from 10 scheme native code compilers. The box plot, lots of box plot. And lower value is better, and 0 means average. The native code compilers are Chess, Bigloo, Icarus, Pyket, Gambit, Larceny, Racket, Nash, Chicken, and MIT scheme. And the values shown below the names are the geometric mean, normalized to the Guile's bytecode interpreter, not Nash. The green points in the graph are the score of Nash. And 14 benchmarks until here, Nash performed better than average, and not so bad, I suppose. And Nash shows the best score in string, but interestingly, that the Guile bytecode interpreter was faster than Nash. So the bytecode interpreter is so fast in string. And another thing is that parsing benchmark was the slowest for Nash, but the PyKit implementation shown here did not show so bad, not so bad. It didn't perform so bad. The PyKit is another tracing JIT implementation scheme. So the poor performance of parsing is probably not due to the tracing JIT, but it's Nash's own fault. Now I'm summarizing the pros and cons. The advantage, obviously, it works really good with tight loop with floating point arithmetic, like 50 times faster if things went good. And the same program could be run. No need to use these kind of type-specific arithmetics. That's, I think, another point. Since not much difference is, as I said, when the program uses C function, there's not much benefit from compiling to native code, and like those large amount of conditional branches like parsers, interpreters, and compilers, it's not working so good right now. And another is that because it's a JIT, it has a warming up time. Like running simple script, in my machine without JIT is like running a hello world will take 20 milliseconds, but with Nash it's like 110 milliseconds. So that's all from me, and any questions? Yes?
So, Guile 2.1 recently gained flow and unboxing. But apparently flows in your Mandelbrot examples were not being unboxed.
Ah, yes, that's true.
Exactly why that happened.
Good point, because not always working well. The unboxings, it needs, sometimes it needs to box it back to return to the beginning of the loop. Yeah. And that part I'm not, the current implementation is not handling well.
Case, I would expect it to be unboxed at the beginning of the loop and unboxed back at the end of the loop on the last iteration.
I'm sorry, I might not understand what you said.
In the Mandelbrot example, I would expect flowmans to be unboxed for the loop iterations, unboxed only when we exit the loop.
How many?
Boxing should happen only when we exit the loop.
There's actually some more things to do. Like when you're going, you need to, when GERD fails, you need to recover the state. And at a certain point, it sometimes requires to save the boxed value before overwriting them, because there's a limited amount of registers and memories, and to recovering state is quite tricky. Yes?
I wonder, your example, when the tracing started, it was lucky in that it found the point that it started.
Yes, that's true.
But when does it give up, and how does it, if it just doesn't hit that anymore?
Giving up is, there's parameters, lots of parameters to control how the tracing give up. Like, well, in reality, the traced instructions could be differ from the naive input value from the caller function, and how do you say? It can take different paths, and if I know, when giving up, it's just comparing the beginning bytecode IP address. And if certain bytecode IP address hits the certain amount of trial error, it's give up and marked as blacklisted. Yes.
Some JIT compilers have a notion of garbage collection save points where objects are so that garbage collectors can easily find which are the origin. Do you have any such considerations about origin?
I'm not sure about other implementations, but in this case, the shared state with the interpreter has top and bottom pointer. And those pointers, inside those pointers, it's safe to store the values, but getting out from going below the bottom and going up the top is unsafe, and the native code need to understand those two pointers when executing. I might not answer your question, but that's how it works right now.
You hold the pointer in the register.
Mm-hmm.
Are you sure that the garbage collector can find?
The garbage collector using Nash is same as Guile, and it's done in C library, libgc. So I made no modification to that part.
So C function can always find native code, native registers to. So is there can be there object which is only pointed to by native code machine register, which can't be seen by C.
I
believe actually Guile uses the Boehm GC, which is conservative, and so it doesn't actually need to track.
yes.
So one thing that I have missed in your talk is that you detect the output, and then you detect that you need to compile it. And you compile it according to the value you have already in the stack and the internal of the machine. So you generate one version of the loop. And how do you manage the situation where you will enter the same code with different data sets, with different types?
Aha. I didn't explain, but it does type checks before running the native code.
And then do you generate a new version for...
Possibly. Like,
And when do you take this decision of generating a new version?
and I didn't explain again, like in the guard has a counter. After a certain amount of number of exit from same guard, it starts tracing from the guard.
Okay. And does this support multi-threading?
Sorry?
Does your framework support multi-threading? Several parallel threads running in parallel?
Theoretically, yes, but I haven't tested so much. Probably it's kind of tricky, so there should be lots of bugs.
Because I can imagine nasty effect where you have two threads that run in parallel, the same code with different types for the values.
That's not a problem because it does type checks and it finds the native code with matched types.
Yes, but I imagine that it will be correct, but you will keep compiling for new
yes,
types.
true.
So you will have a tremendous slowdown in performance in such situation. I can imagine that.
That's a good point.
You have no experience with that you could share with us today.
I don't have right now. Yes?